Afternoon everybody, it is afternoon I think now. I'm here to present the LINK project. This is in collaboration with CFAS, Imperial College, and we also had a number of commercial partners that were heavily involved throughout the whole project. The project is still running till March next year. John, you actually touched on this a couple of times. To put any devices in the environment you need a licence. This is actually the Wildlife Northern Ireland Order 1985. It's actually an application for a wildlife licence to kill, take, disturb, transport. So in order to get this, you need to do an environmental impact assessment before you can get a licence. This is sort of what has driven the project of LINK. The reason why we derived the LINK project in general is because of the way that we need to do impact assessments at the moment. At the moment they're very time consuming. If anybody has had to go through the process, they can go between months to years to actually do an environmental impact assessment. They're very reactive. You're obviously doing it before the tidal or wave device actually goes into the environment itself. Extremely costly. I believe looking at the MCT website, they spent over $2 million on an environmental impact assessment for their, while SuperGen actually was, before it even started running and during, so it's very costly. And the other issue or problem is that the environment that these devices are actually going in are very high energetic flow environments. The organisms that live in them have to be able to tolerate quite high forces of waves or tidal currents. Therefore, to test any significant difference between when you put the device in versus a control is very difficult to statistically test. So that was sort of the driving of the LINK project. It's basically to be able to demonstrate the ability to numerically model changes in ambient hydrodynamics resulting from either wave or tidal energy devices, installation of large arrays in effect. And then using these hydrodynamic models that we have all developed, and we've seen quite a lot of them today already, how we can link these or couple these to ecological models to be able to predict changes in lots of different ecological processes such as the benthic habitats, plankton growth and dynamics, plankton transport, as well as fish communities. So, just going back, the actual approach, we've obviously looking at hydrodynamic modelling. We did this by testing two different software. We're using Fluidity, which is by Imperial College. It's open software and freely available for, and I believe a number of you are already using it. And the other software package that we used was Mike by DHI. It's a commercial software package, and we'll be able to compare and contrast the two different software packages. Once you're getting these hydrodynamic models, obviously you need to link them to ecological processes. In doing this, we're using different ecological modelling approaches. The first one is particle tracking. It's used a lot in ocean oil spills or oil pollution studies. We're seeing whether we can use particle tracking also to look at influences on organism transport. NPZD models, so nutrient, phytoplankton, zooplankton, detritus models, important for biogeochemistry, but we're also looking at bigger biogeochemistry regional models as well. We at the moment have got just singular devices, and we know that you can model around the actual device itself, but obviously we need to look at a range of spatial scales. Environmental impacts will occur not only just at the turbine scale, but also at potentially areas effects, which is up to 10 sort of kilometres away, but you can also get regional effects, potentially up to tens of kilometres away, 100 kilometres, all along coastlines, which I'll show you shortly. So the effects will be obviously at different length scales, and we need to be able to, we can obviously model this at a range of scales. So going to the actual hydrodynamic modelling, this is work that's been done and carried out by Imperial College. There's a lot of really good work they've been doing on array optimisation. Just showing you here, it's actually not, no. There's, obviously the video's not quite going, but basically if you put in a lot of arrays or turbines, there's going to be an effect on the hydrodynamics. And so what Imperial College has been doing is if you change the array optimization, how does that change power extraction? So above here they've got the placement of the turbines. There's actually the round circle is an island. This is sort of more a complex tidal area. And then just looking at the effects of, or basically what the array is doing is optimizing to power extraction, which is what that graph is showing. So each iteration the turbines will be moving and this will improve the power production. The really useful benefit of this particular tool is that it's not just only for looking at power interest, we can actually use it also to look at environmental impact. So basically you could actually block off an area and say that's very sensitive to changes of velocities below or above X, Y or Z velocity, and then how that turbine array will change that or not change it. So it will move depending on the on whether it's going to affect a certain area or not, away from the devices itself. Just moving on to organism transport, they're all the things you can't see in the ocean. They're the microscopic plankton, as you like, the animals, protists, algae and bacteria. They can be transported very large distances in the ocean. Of course they need water motion to do this, but how will arrays, and we're talking like hundreds, big scale array distribution, how that influences organism transport. People probably don't realise, but the organisms, even though you can't see them, but they actually support a wide range of higher trophic levels, ranging right up to the big whales, right down to the small invertebrates that are on the benthic sea floor. The other importance of water motion on transport processes is actually they assist in dispersal processes. So it's really important for, say, reef connectivity, so if larvae can get from one reef to another around the system, whether that changes, whether that will be influenced. So even though we're talking about big high velocity areas or large wave energy areas, as we're talking about what happens further on down the coastline where you get a lot more sheltered areas where the changes in hydrodynamics will influence this. So what we've done is we've looked at this through particle transport modelling, and I'm just going to briefly explain. But basically we've had an idealised model. We can look at different turbine configurations in a channel and look at how that impacts down scale of that. So basically where mass, there's almost 95% accumulation. This was in a basin that we had. It was, I haven't put the whole figure in, but basically you've got a maximum of 5% change. Whether that's an impact or an effect, that still needs to be, we need to be able to validate, but unfortunately we haven't got this is just to prove whether we can use transport particle tracking model to look at these types of particle transport work. And then moving on to the further work that's just recently been submitted, and this is by CFAS Johan van der Molen. He's basically developed a large biogeochemistry model, the 3D Getum-Ursum BFM Northwest European Shelf model, and it's got a 5 kilometre resolution, so we're talking a very large scale model. It has 25 layers within it, and he tested 2 scenarios. So basically looking at the Pentland Firth, the licensed power extraction at the moment with 800 megawatt, which is evenly distributed throughout the Pentland Firth, and then this is what it would be if it was at the licensed power, but just to see if we can see big effects, what happens if you times that by 10 to get, say, an 8 gigawatt license area. In the model, it's very large and been able to investigate a lot of different processes such as currents, tidal elevations, temperature, salinity, primary production and benthos. So there's not enough time today to go over all those processes, but basically just to look at the tidal elevation here, obviously this on the left-hand side is the just the 1 times effect, so basically when you've only got the actual licensed amount of tidal arrays in there, and as you can see, although there is a little bit of an effect, it's what they classify as a minor effect. We're talking about a 1 centimetre difference in tidal elevation. The interesting thing that you can see here is that it is actually affecting right down the coastline of the UK. It's not just actually what's happening at the Pentland Firth there itself. Is there actually On the left-hand side is when you've got a lot of turbines put in, and what happens, and obviously there is up to a 10% change in the area where the tidal turbines are for sea surface elevation, but interestingly again you can see a lot further down the coast. So there is going to be an impact, but that's at 10 times the amount, and I don't think we'll ever get to that stage. We're just seeing if we could actually see something going on. The results for, if we look at nutrient and primary production, which are also two very important processes in the environment. Nutrient supplies nitrates to all the microalgae and also all the plants so that they feed high trophic levels, and obviously the net production of for carbon input. Basically the top graphs there are showing just the control with nothing in it, with no turbines in them, and then when you increase it by 10 times the amount, 1 times there's very little difference between when you've got turbines in or not, but if you times it by 10 times the amount, then you have up to, again, it's about 10% difference in both primary and nitrate production. So, and as you can see, that's actually the North Sea. So there's actually differences within the North Sea, not in places you would expect, not just the coastline, but actually within the North Sea itself. So quite important. So just to conclude, we've basically shown that you can use all the different ecological modelling tools to model a range of ecological processes, ranging from both the small phytoplankton right up to the large biogeochemistry models. You can model the processes at a range of spatial scales, which is very important for environmental impacts at the device scale, far field and regional effects. And the models identify, what the models will allow us to do is identify areas that actually need further experimental work. So if we find that it doesn't matter what you do with the models, that area is not, you could give it the worst case scenario, but it's not going to have an effect. But the ones that show that there might be, that's where you need to go out and actually do some experimental field work and validation of the models. And this is actually quite important for us in that we had good collaboration through all the partners. It was a large group of people, and we also had really good collaboration with all the stakeholders, which actually fed us, or gave us a lot of feedback throughout the whole LINK project to provide the results that we've, some of the results we've provided today. So thanks very much.
This production is brought to you by the University of Edinburgh.